Good afternoon, everybody. Um, this is the review session for our second exam for this class, Facilities Planning, IE4355. And as we did for the first exam, we're gonna walk through the format of the exam, and also we're gonna discuss the topics that are going to be included as part of the second exam. So I'm recording the lecture, I'm recording the review. So as soon as I get the video link, I'm going to upload the link to the modules in Canvas. So in case you want to watch the video again, or if you want to watch the session again, you will have access to it maybe in a couple of hours. That being said, let's get started. Feel free to ask questions. You can send me a message via the chat, or you can just unmute yourself and ask questions as we move forward with the review. So we're going to start with the format. The format is going to be very similar to the format of the first exam. So in section 1, we're going to have 10 questions that can be multiple choice or true or false questions. So those are 2 points each. In section 1, the total will be 20 points. Section 2 has 3 topical problems. These are going to be similar to the problems that you solve as part of the homework or the assignments, and also in the labs. So these 3 problems, I decided to do 3 problems because these are time-consuming problems. So I will say 3 will be enough for the time period, or for the time that you're going to have available to work on the exam. So this could be short answer, explanation, description, or mathematical. For this second exam, the majority, I will say all of them will involve some type of computation. So again, the best way to prepare for section 2 is to go over the assignment, and also over the labs that we cover after the first exam. So in terms of the material, we started this second part of this class with lecture 5, in which we discussed the supply chain management and how that impact the facilities planning. So we started with answering the question, what is supply chain management? And also a framework, a supply chain strategy framework. We also talk about the components of a supply chain management and the major obstacles and common problems associated with supply chain management. So for this section, or for this lecture, you should expect some of the questions of section 1, the multiple choice or true or false questions, to be associated with this lecture 5. So my advice is for you to go over the material, review it, and then again, you should expect 1 or 2 questions from the multiple choice associated with this material. In terms of the next lecture, which is space requirements and layout, in this lecture, we study structural system performance, enclosure system, atmospheric systems, electrical and lighting systems, and life safety systems. So for lecture 6, we did multiple problems associated with the atmospheric systems in terms of designing the capacity for your facility in terms of heating and cooling. So those problems, those type of problems are going to be part of you should expect at least one problem associated with that material. I'm going to be providing you with the coefficients that you are going to need to solve those type of problems. So those coefficients are going to be given. I'm also providing tables and any data that you will need to solve the problems in the exam will be provided. So that includes those coefficients that you will need to solve the problems associated with the atmospheric systems. So that's lecture 6.
Quick question.
Yes.
Is that going to also include the equations too?
Yeah, so for the atmospheric system, there's just one equation. So in terms of, I mean, I think you can easily memorize that one, but if you need me, I can include that equation as part of the exam. But yeah, I will say yes, I can include that equation as well.
Okay, thanks.
No problem. Any other question? Okay, so let's move to the next slide. Lecture 7, we discuss personal requirements. We talk about the employee, the restroom design, office facility planning, and barrier-free compliance. As part of the design for the employee, we also discussed the design of parkings for a facility and determining how many spaces you will need and how can you design a parking space for your facility. So we did a lab on those. We have a problem in the lecture, so you should get familiar in terms of how to solve those type of problems as well. For the rest of the topics in this lecture, you should expect questions related to those topics. I mean, restrooms, in terms of the design of office facility planning, the different type of office designs, and barrier-free compliance in terms of some of the design requirements related.
You're breaking up a little bit.
I'm sorry. So what I was saying is, can you hear me now better? Can you hear me now?
I don't know about everyone else, but you're breaking up for me a little bit there.
Yeah, you've been breaking up for me too.
Yeah, me too.
Okay, let me find out what's going on.
It's better now.
Yeah, it's better now if you want to just start from like restrooms again.
Okay, good. So let me know if you start cutting again. So personal requirements. So in terms of the material covered in this lecture, you should get familiar with how to design a parking for a facility, and we cover a couple of examples as part of the lecture and also as part of your labs. So the solution for the lab is posted already, and I think as part of the review, I also included a problem that we can go over as part of this discussion. For the rest of the topics, restrooms, office facility planning, and barrier-free compliance, you should get familiar with the different type of office designs. Also, what are some of the requirements for barrier-free compliance, and so on. So those are relevant, and those could be questions related to the multiple choice or true or false for section 1. And then finally, we get to lecture 8, in which we study scheduled design. Here we talk about the marketing information and how is that linked to our design in terms of schedule, the process requirements, and also how to compute the number of machines that we will need for a specific process. So again, you can expect to see a problem similar to the ones that we observe in the lecture, and also in the assignment related to the machine assignment problem, computing the number of machines that will be needed in terms of the process that you are going to be having in your facility. So those are the lectures included in this second exam. These are, I will say there's not a lot of material in terms of the number of lectures, but there are several different type of problems that you should be studying in order to do very well in this exam. So again, make sure that you go over the assignments and also over the labs that were covered during this second portion of the semester.
Quick question for lecture
Yes.
machine assignment problem. The homework that was due today, is the solution going to be posted for that before the exam?
Yes, I'll be posting the solution today.
Okay, thanks.
I guess for that same assignment, just to see if I understand it correctly, when we like are looking to see if M is in Mike is less than N is in Nancy prime is or greater than, do we just like picking, is that just like rounding the integer up? So like for instance, I got like 4.1, so I would just calculate it at 4 and calculate it at 5 machines, and then you just evaluate the numbers from there to figure it out.
Well, if you get a fractional value, like a decimal point, 4 point something machines, you should always round up. So you go to the next number. So if you get 4.3, 4.5, 4.1, you should always round up to the next machine. So that will be 5 in your case.
Okay, and that holds for like the second problem of the homework that was due today. It was like trying to calculate the downtime. That holds for that sort of problem as well.
Second problem, let me look at it.
Yeah, it was like 4 machines per operator, or I could do 5 machines per operator, and then it was all about like calculating the downtime for the
yes.
machine.
So for those, yeah, I got you now. So for those you have, I mean, it's going to be depending on the specifics of the problem, and you will have to look at you're gonna have to determine specific range for which you're gonna assign 1 machine to an operator or 2 machines to an operator, and that will depend on the idle time. If there's any idle time for the operator, or if the operator is mostly busy, you know that you are limited in terms of the number of machines that you can assign to that operator. But let me just open the solution for that, so we can go over that. Yes, so I got it here. Got it here. So so you're familiar with the problem. The question is, what is the maximum number of machines that can be assigned to an operator without creating machine idle time during a repeating cycle? So as you mentioned, the results for n prime will be 4.16. So now you have to make a decision on whether you assign 4 or 5. So you know that if you assign 4, you will probably, I mean, this operator will have some idle time associated to it, right? Because that 0.16 is telling you that you can assign more machines to the operator. So if you go above that, if you assign 5, you know that this operator will not be able to handle those many machines because of the time availability that the operator has. So 4 is going to be the maximum number of machines that can be assigned to an operator without creating idle time during a repeating cycle. So idle time in terms of the machine, as I mentioned already, if you end up assigning 5 machines to this operator, there's going to be a point in which the operator is not going to be able to get to one of the machines on time. So the machine is going to have to wait until this operator is done with the fit machine. And then he will have to go after that. And that period of time in which the operator is handling machine 5 is going to be idle time for machine number 1, if that makes sense. So 4 in this case is going to be the maximum number of machines that you can assign to this operator, meaning that you might need, if you have more than 4 machines, you might need to have an additional operator to handle the rest of the machines. If you go above 4.16 or 4.16.7, then you know, if you go to 5, for example, then you know that based on these computations, the maximum that you can assign to this operator is 4, almost 4, close to 4. So if you go above that, you know that the operator will do the work, but that will mean that one of the machines will have some idle time because the operator will need more time to get to all the machines. So hopefully that makes sense.
Yeah, that makes sense. I think I just made it harder on myself when I calculated it at 4 and at 5 and then determined that it was 4. But I guess it makes more sense just looking at it like this and being like, okay, that's 4.
Okay, good. That's a good question. So hopefully that's clarified. And let's go back to this. So in terms of how to prepare for the exam, as I mentioned already, study the lecture slides, the labs, and the homework. I will provide the formulas and tables needed for, and the coefficients that are needed for solving the problems. The exam is closed book and notes. Link to access the exam will be available in the Canvas module at the time of the lecture. Clearly show your work and all formulas using your solution. This will help me award full and partial credit. Multiple choice true or false questions will be answered in the computer. And then you're going to have 3 problems in which you're going to have to upload a file. So my advice is that you work the problems in a paper and then you take a picture or scan that sheet of paper with the solution, and then you upload that file to the system. As always, I will provide you with 15 minutes, additional 15 minutes to upload the files. So your exam is going to start at 5 o'clock. Then if you take the whole period, will be 1 hour and 20 minutes. So you should be working on the exam until 6:20, and then you should use the time after 6:20, which will be additional 15 minutes to upload the files. So you will have until 6:35 to upload your files. The exam will close at 6:35. So if you have, again, if you face issues uploading the files to Canvas, you should send me an email during this time period. Let's say by 6:30 you have tried and you have not been able to upload the file. So at that point, send me an email, include the files. So I'm aware that that's an issue and that you have completed the exam. The only thing that is missing is just uploading the files. So that's in case you are facing issues uploading or the system is creating issues for you in terms of not letting you upload the files. And then here's some questions. I selected these questions from your assignments and your labs, just to give you an idea. Yes.
Real quick, for the exam, is it going to be like last time where do we need to be in the actual Zoom link, or is it just on our own and then submitted on Canvas?
You're going to be by yourself. So it's just going to be like last time.
Okay, thanks.
So these are the type of questions. These are problems that I selected from the assignments. Could be similar to the ones that you are going to be seeing in the exam. So this is to compute the heat loss of a facility. So for this type of problems, you have the heat loss, or you can compute the cooling needs for the facility. So in this example, I'm showing the heat loss. And then you have the inside design temperature is 72 degrees Fahrenheit, and the outside design temperature is 12 degrees Fahrenheit. And then we also have some additional information about the facility, the area, the height of the walls, and no windows in this case, and then 6 glass doors. So again, the expression that you will be using to compute the different coefficients for the floor, the roof, the glass windows, the doors and the walls, and infiltration, those are going to be given, as you can see in this table to the right of the slide. So I'm giving you UF, UR, UG, UD, the EUW, and UI. So those are going to be given. The equation at the top, I'm also providing that information. So the only thing you have to figure out is how to implement this information into computing the heat loss for the facility. So for instance, in order to compute the heat loss through the floor, you need to compute the area and then multiply the area of the facility and multiply that by the coefficient, and then also multiply that by the difference in temperature from inside and outside. So 72 minus 12 in this case. So that will give you this coefficient. My advice for when solving these problems is that you make sure that you have the right number in terms of, I mean, if you're going to be using this scientific notation, that you are counting the exact digit, the exact number of digits when you're placing this coefficient when using the notation. So in this case, that's 5.83 times 10 to the power of 6 BTUs an hour. So make sure that you use the right notation. That's what I'm saying, because if not, at the end, you will have the wrong result. Then we have QR, which is the heat loss through the roof. So again, the area is needed. So same area, and you have the coefficient for the roof and the difference in temperature. For QD, this is the heat loss through the doors. We have 6 doors. We have the area of the doors, so it's 6 times 24, the coefficient of the doors times the difference in temperature. QW is Q for the heat loss through the walls. So we have 2 different sizes in terms of the walls for this facility. So we have 2 walls that are 400 times 20, and then 2 walls that are 300 times 20. So that's why you have these 2 areas, 2 times 8,000 and 2 times 6,000. And then we are subtracting the area for the doors, because we are already taking those into account with the QD. So we are subtracting the area for the door, so that's 6 times 24. Multiply by the coefficient for the walls and multiply by the difference in temperature. We get to QI, which is the heat loss due to infiltration. So in this, we are going to be using the area again, representing the ceiling or the roof area, plus the area for the areas covered by the walls. So in this case, that's going to be 120,000 for the roof. And then we have the 2 areas, the 2 separate areas for the walls. And then that's multiplied by the coefficient and also multiplied by the difference in temperature. And after getting all these coefficients, we sum in order to get that heat loss for the facility. In this case, that's 9.7 to the power of 6 BTUs an hour. Any questions? Yeah.
Yes, sir. What were the ones to say they were going to be given? It was like QW or D and I?
The parameters or the coefficients that are going to be given are the U coefficients that are on the right. You see that table?
Gotcha. Yeah.
UF,
Oh, okay.
UR,
Okay.
yes, those
We just
coefficients
gotta
are going to be
calculate. Okay, so we still have to calculate all the other, the
yes,
QRs. Okay, I got
yes,
you.
correct.
Thank you.
No problem. Any other question? Good. So next problem. This is coming from the last assignment, or assignment 5. In this one, we have a part that requires 3 processing steps on 2 machines in sequence ABA. So there's 3 steps in this process, but as you can see, step 1 and step 3 are requiring the same type of machine, or require the same type of machine. So in this case, machine A. The demand for this part is 10,000 units per week, and the company operates 6 days per week, 8 hours per day. So given the following performance data, find the number of each machine needed to meet the demand. So for operation 1, operation 2, and operation 3, we have the machine type that is needed, the standard time, the efficiency of the machine, the reliability of the machine, and the percentage of defects. So in order for us to solve this problem, we first need to figure out what will be the input required for each one of these operations. So we have the way this is solved is, in this case, I have named processes or operations requiring machine A. I have named the first process A1, which is the first step in the production process, and A2 denote the last step. So for A1, which is the first operation, I can easily compute the input by using the equation that we discussed in the first part of the semester, which is the output that is required for the process divided by the multiplication of 1 minus the defects for all the machines that come after this first operation. So in this case, we have D1, D2, and D3. D1 is associated with the first operation, D2 with the second operation, and D3 with the third operation. So O3, which is the output, in this case, 10,000 units per week, divided by the multiplication of 1 minus D3, 1 minus D2, and 1 minus D1. So for the first operation, the required input is 11,423 units. We have to do the same thing for the second operation and the third operation. So for the second operation, again, we are going to look at the defects for the third operation and second operation. The defect rate is 5%. So we go above 10,000 divided by the multiplication of 1 minus D2 and 1 minus D3. And I think there's a typo in this solution. If I'm not mistaken, this should be 0.95. I'm sorry. Let me check that. Yes,
Yeah, Professor.
Is that right? Should be 0.95 and 0.95. So just make a note. This should be 0.95 here. See if I can fix it.
Yeah, Professor, I have a question.
Sorry?
Yeah, I just had a quick question. When you say on those, like the standard times, are those like the cycle time basically for the machine, right?
Standard time, yes, is the processing
It's
time.
the same thing. Yeah.
Processing time for the part in that machine. Yes.
Gotcha. Thank you.
Yes. So this should be. Let me fill this. So you see what I'm saying, what I'm doing here, right? Like 0.95 times 0.95. And then that will be 11,080 units. And then for A2, which is the last operation, we are also computing the input needed for that operation, 10,526 units. So now that we have that, we can compute the number of machines needed for each one of the operations. But remember, in this case, my operation 1 and 3 are requiring the same type of machine, which is machine type A. So before we get into finding those numbers, remember that you have to use the same units. So in this case, we are working with minutes. So in order to get H, we have to look at the information that was given. We have information in terms of the number of hours a day, the number of days per week, and we are transforming everything into minutes. So in this case, it's 2,880 minutes per week. So using this, we know that the input that we found for each one of the machines is what we are going to use for the Q value in this F formula. So knowing this information now, we can solve for the number of machines needed type A, which is the first line that we have here. We have the summation. So there's a summation here, one for the operation number 1, and then this is for operation number 3. So we have the information for operation 1 and operation 3. We have the input that is required for operation 1 and operation 3. And we are summing those two because we know that they have the same type of machine. So for machine type A, we end up with 31.57. And as I mentioned in our previous discussion, if we end up with a fractional number, we have to round up, right? So in this case, we are gonna need 32 machines. It's impossible for us to have a fraction of a machine. So that's why we round up in this case. And then for operation number 2, we follow the same process. Now we use the input for B, which is 11,080 units. And we substitute that into the equation and we end up with 12.79. Again, we round up because we're gonna have a fraction of a machine. So the solution for this problem we have for the number of machines type A we need is 32. And the number of machines type B that we need is 13. Any questions? Good. So let's move forward to this one. So this is the problem that we solve as part of lab 4. So here you are asked to design a parking lot that is 400 feet wide, or you have a space that is 400 feet wide and 370 feet deep, and you are asked to design a parking lot using this space. And for this type of problems, I'm going to let you know exactly the type of design that I want you to perform. So for example, the number of standard size cars and the module that you are going to be using. So in this case, in this problem, I'm asking you to work with standard size cars and to work with the W2 module. I'm also providing you with additional information, so like 90 degree angle for the parking. And using this information, you can search for the space that is needed to accommodate this type of module. So in this case, every module, if you look at the table for standard cars, which are they require a width space of 8 feet and 6 inches. With a 90 degree angle, a W2 module will require a 66 feet width. Okay, so W2 module, 66 feet width for the space. So knowing this information, and again, I want to mention this area that we have is 400 by 370. So the number of modules that you are going to be able to fit is based on whether you want to use the 400 dimension as your width or the 370 feet dimension as your width. In this case, I use the 370 feet. Okay, so by design, it's going to be based on that decision. Okay, and this decision can be based in many aspects of your facility, like for example, where the entrance of the parking facility is, or where's the main street located. So typically, if you have a main street running, let's say on the right side of this square that I'm showing, you will tend to design this parking in this way. So based on that decision, if you're going to use the width at 370 or 400 feet, then the design is going to, the number of spaces that you're going to be able to fit is going to change. So in this case, if you divide 370 feet by 66 feet, that gives you 5.6 modules. What that means in my case is that I can fit 5 modules easily in this area, and I can also fit half a module as part of my design. So I round down to 5.5 modules. And we know that each module has 2 rows. So for that half a module, I'm going to have only 1 row. So based on that, you see how my design is going to look like. I'm going to have in red 5 modules, 5 complete modules, and then in blue I have a half a module. So now, knowing that each red module is going to fit 2 rows of cars and the blue module is going to fit only 1 row, I can determine how many cars I can fit in each row. So for each row, you know that the width of the vehicles is going to be 8.5 and 8.5 feet, and I have 400 feet of space. So if I divide 400 by 8.5, that's about 47 cars per lane. So that's going to be 47 cars per lane, and that's without the circulation lane. So I have to take into account also that those circulation lanes in my design. So if you see in my draw, you see that there are some green lines that are cutting the red lines. Those are used to represent the circulation lanes. And I'm going to have to lose some parking spaces in those lanes because I need that space for circulation. That's going to happen in that's not going to affect the first row. You see that first row can go from side to side, and that last row, that the one that is blue, is not going to be affected by the circulation lane. So those are going by corner to corner, but the rest of the lanes will be cutted because they need some of that space for the circulation lanes. Okay, so adjusting for 2 circulation lanes, lane 2 will handle 400 minus 15 feet times 2. So 15 feet is the space that you will need for 1 circulation lane. So we need 2. So that's why I'm multiplying times 2. So 400 minus 15 times 2, that's going to be the space needed for that you're going to have available divided by 8.5, which is going to tell you the number of parking spaces that you can fit on those lanes in which you have a circulation lane. So in that case, that's going to be 43. So now that I know how many cars I can fit in each lane, I can compute the total number of spaces. So if you see in my picture, I have in blue, I have some numbers in blue, 1 through 10, and then on the top to the left, I have an 11. So I have a total of 11 lanes in which I can accommodate parking spaces. So, but for rows rows 2, 3, 4, 5, 6, 7, 8, 9, and 10, we will only fit 43 parking spaces because those lanes are cut by the circulation lanes. And then I'm going to have 2 lanes, the one at the top and the one at the bottom, in which I can accommodate 47 cars because those are not affected by the circulation lanes. So in total, I have 43 times 9, 387 spaces, and 47 times 2, 94. So 387 plus 94 is a total of 481 parking spaces for this parking design. So that's the answer for this exercise. Any questions?
Yeah, for problems like this, if for some reason, if say we did ever tackle this in the real world, when do we take into account, like, should we angle the spaces or not?
That's a very good question. So in practice, you will do multiple designs in which you will consider whether, let's say, let me start from the beginning. You will have a forecast in terms of how many customers you will expect in your facility every, I don't know, maybe at the peak hour. So that should give you a starting point in terms of knowing how many cars you will have as an upper bound for your facility, and you will try to accommodate as close to that number as possible. So when you have an angle, you are able to save some space. I mean, you save some space when you design as an angle. So that will allow you to accommodate more cars. However, when you design with an angle, I'm sorry, you also are most of the time limiting the direction of the flow. So typically, if you're designing with an angle, you want cars to go in a specific direction. So those are the drawbacks, and the advantages is that you can accommodate more cars, but the disadvantage is that if you design using an angle, you might need to limit the flow to go in just one direction. So starting with the forecast, knowing at the maximum or at the peak hour, how many customers or how many employees you're gonna have in your facility. Starting from that number, then you should have, you should try to accommodate as many cars as possible closer to that number. So if you have flexibility in terms, let's say you have enough space to accommodate all the cars that you would have at the peak hour, and you have the option to provide the employees with a design that is more comfortable, in which you can allow them to have more space, or you can allow them to go in both directions, then you will start losing up on those requirements. So again, it's going to depend on the actual situation. If your goal is to accommodate as many cars as possible, then you have a limited space, then most likely you're going to end up with a parking design that is in an angle in which you are going to limit the flow to go in just one direction for most of the lanes, and which is what you see typically if you go to HEB and these stores that are typically full most of the time. You will have this direction parking spaces in which you have flow in only one direction. But if you have flexibility, if you have enough space and then you want to create a design that is more comfortable for your employees or your customers, then typically you will go for a 90-degree in which customers can move in both directions and have the flexibility of moving around without constraints. So I don't know if I'm answering your question, but those are the conditions, and those are the aspects that you have to take into account when designing a parking space.
Thank you.
No problem. Any other question? Okay, good. So again, I'm going to be posting the video in a few hours, so you can check on that tonight. Also, I'm going to be posting the solution for assignment 5. And if you have any questions, feel free to send me an email and we can talk if needed on Wednesday. And I also, so we need to set up an appointment on Wednesday. We can do that. I also have office hours on Thursday. So feel free to connect during my office hours, or again, if you cannot connect during the office hours, send me an email and we can set up an appointment. Okay.
Thank you. Have a good evening.
Okay, you too. Bye-bye.
Thank you. Bye.